Good afternoon. This is CIVE 634, Surface Water Hydrology, and I'm Professor Victor Ponce with the Department of Civil Engineering at San Diego State University. The subject today is the Clark unit hydrograph, and perhaps with enough time, we'll get into the subject of cascade of linear reservoirs. So today we're going to, I'm going to cover the G09 and G10 and probably G11 also. And I intended to get to G12, but G12 is going to be a short one. And then hopefully we'll get to G13. Even if we don't get to G13, it'll be fine. We're still within the mark here. So let me get first, let me just, before I get started here, I reiterate that the subjects that we're going to cover today are not easy. They require a lot of attention and study. They're unsteady. It's unsteady hydrology, not even hydraulics. It's unsteady hydrology. Well, it's kind of somewhat different, but it is unsteady hydrology. We're looking at catchment routing, and catchment routing is generally considered to be hydrology. Okay, with that I want to say at the beginning that, let me see. Yeah, right. I'm going to say at the beginning that there are two processes, I guess you could say primary and secondary processes in physical processes that we're going to track in catchment routing, as well in all routing, as well as in channel routing too. The first one is termed convection or concentration or translation. Those three words are used. And the second one is called diffusion or attenuation or storage. Those three names are used for these two processes that are quite distinct. The distinction is because convection or concentration or translation is a first order process. That means it arises from a differential equation. It's a partial differential equation of first order. It doesn't have any squares, while the diffusion is a second order process. Diffusion, storage, attenuation is a second order process. There is a third order process too. That's a third order differential equation, but it's not used in practice. It's considered to be part of theory. I've written a couple of papers on the third order equation, and I know other people have, Ferrick and others, but to this day, that stuff has not gotten to practice because it's very small and mostly can be neglected. I think I already told you that an error of 20–30% in hydrology would not be uncommon, given all the ifs and buts that there are. And here in the third order, we're talking maybe perhaps 1% influence or 2% is too small to consider. So let's not concern ourselves with the third order process, but with the first and second order, we have to. Okay, so that's what we're going to be talking about today. And no better example than the Clark unit hydrograph, because in the Clark unit hydrograph, as we already covered, first it does a time area method, which is a convection, a first order process. And then lacking the second order, Clark decided to introduce a linear reservoir into the calculation. And he did it successfully. And he was working at the time for the Army Corps of Engineers. He was, I believe, an employee of the Army Corps of Engineers, and they liked his method. And it's a method that is very much used in Army Corps of Engineers practice. And it will be apparent later on because I'm going to be returning to talk bad about U.S. Army Corps of Engineers practice as far as the Clark unit hydrograph. Okay. It appears to be an old method, 1945. However, it was in 1998, I believe. Let me see. 1998. It was resurrected. Well, it never died, but it was brought back into the forefront of hydrology in this paper called "The Evolution of Clark's Unit Hydrograph" or Clark Unit Graph Method to Spatially Distributed Runoff. And that's why I have brought this paper for us to briefly look at. We can't read the entire paper because it's difficult. We spend a lot of time, we probably wouldn't get much, but I'm going to touch base on that paper. That's G12 in our syllabus. So let's go back in here then to the GO9. Okay, the story behind GO9 is the following. As I already mentioned, but let me reiterate. In 1989, or prior to 1989, I was writing my hydrology textbook, which I designed to be an undergrad, beginning grad textbook, mostly undergrad, beginning grad. Why do we say that? Because sometimes hydrology is not taught at the undergrad level. As a matter of fact, at San Diego State is not required. They require a course in hydraulics, a course in this, and a course in that, but they don't require a course in hydrology. Hydrology is a fundamental thing. Why is that is not covered? The answer is that the curriculum is full. We don't have any space in the curriculum. We got to limit the requirements. It used to be 135, 136, but now we're trying to reduce it to 128 to make it all uniform throughout the United States. So we are against a space problem. I mean, we meaning academia, the university, the school. We don't have space to put courses. So some courses would have to be considered to be elective. And hydrology 445, CIVE 445 is considered an elective. And therefore, a lot of people don't take it, including many in this class. I mean, we don't have to reiterate that. So that is a deficiency, but we have to do the best we can with what we have been, the cards that we have been given. So, so that was the issue of how to write this book. So we wrote it as basic undergrad, but we had to put in some grad because we realized that, like I said earlier, that some people have not taken it. So have not taken hydrology, basic hydrology as an undergrad. Now, I decided to do 3 chapters in routing because I was considered myself the top routing expert at the time. And I think I still am in many ways. And so I expanded the issue of routing into three chapters. Reservoir routing, which was the easiest, then channel routing, a little bit more complex, and then finally catchment routing. And the chapter 10 was catchment routing. And as to what to cover, then I researched the issue of what to cover. And I had to do mostly hydrologic routing because that's the beginning, and then go into hydraulic routing. So we covered first the time area method, then the Clark unit hydrograph, then the Cascada linear reservoirs, and that stops the hydrologic methods. And then we moved on to kinematic and diffusion routing, which at the time, 1989, I had just developed it. I just developed the diffusion wave routing method in 1986. So I obviously included it in my book. And this is interesting that I like to share with you guys. When you do an undergrad book, you must make the subjects relatively easy because they are beginning or introductory subjects. But if you do it right, you should not do all of it easy. Because if you do it all of it easy, you fail to gain the respect of some people that want something more complicated. So we were lucky that at the time we had just developed the diffusion wave routing method. So we put it in the book in chapter 10. In this class, we have briefly, well, we have covered it actually when we talked about overland flow. So I'm not going to go back and talk about that in this section of the course. We already covered it, although briefly. So today I'm going to be talking about the paper that Nicole Nucitelli and I wrote in 2013. And the issue was that Nicole needed to graduate and she needed a study or a special study. And I knew that she was good in math because she had proved that already. So I said to Nicole, why don't you look at the comparison of the 2 types of Clark unit hydrographs and write a paper on it, comparing them side by side and maybe even developing a calculator that would do both at the same time and clearly show the differences between them. Okay, as to, and I'm going to reiterate in here, as to the issue of which one of these types of Clark unit hydrograph is preferred in practice, I have a clear answer to that. If you're running a model that has already been built for you, like HMS, then you're running the original Clark unit hydrograph as put together by Clark. And if you're not running that, and instead you're building a model on your own in an Excel spreadsheet or a computer program of any such sort of thing, such thing, then you could, and perhaps you would, use the Ponce method. Why? Because we have spelled that out clearly in our book, clearly. And therefore, I mean, it's easier to follow. I had an acquaintance of mine, a colleague, many years ago, that talked to me about the content of my book, and he said, Ponce, he said, the Cascada linear reservoirs, which is the kind of related method right after the Clark unit hydrograph, is a very difficult thing to conceptualize. But yet, in your book, it looks easy. He said, that's what he said. It looks easy. You made it easy in your book, and that is correct. We did a step-by-step process, explained everything. So like in the Cascade, we did the same with the Clark. We have a knack for clarity. So the Clark method in my book is transparent, totally transparent. But there is a slight difference between the original, let's say, now, I don't want to call it standard. I don't think that the word is standard. It's the original Clark method, 1945, and our method, 1989. How is it that I differed or deviated from Clark, being Clark an established method? Well, I realized that Clark was established, and yet it was not, because the paper by Clark was difficult to read, difficult to comprehend. And I said, typically, or most likely, most people don't really know it. I said to myself that, and because I know what I'm talking. So I said, if they don't know it, then they're not going to complain when I make a slight modification of it, which is for the better. So that's what I did. I had the decision to make to repeat the Clark method, regurgitate the Clark method as the best as I could, or change it a little bit to make it more amenable to current theory of routing. Because let's recognize that when Clark wrote his method, he knew very little about routing. Routing wasn't really the word in that time, 1945. As a matter of fact, we find it a tremendous accomplishment by Clark that he even did that at the time. That was the time when the hydrologic methods were coming up of age, let's say 1940, 1945. So he was right at the right time, at the right place. But then routing developed more and more, and by the 70s and 80s, it was already a big, large body of knowledge. So with that, without further ado, as they say, I'm going to get into the comparison that we did with Nuccitelli. Comparison of two types of Clark unit hydrographs, Victor M. Ponce and Nicole Nuccitelli. Nicole graduated in the year 2013 or 14, I don't remember, with a master's degree in civil engineering. We say Clark's original and Ponce Clark's are explained and compared. Clark's procedure, why do I call it Ponce's Clark? To make a difference between, actually, our Clark is not Clark's. It's a change or modification of Clark, which leads to a slightly different answer. We knew from the beginning that the answer was going to be slightly different. And what we did in here, many years later, by the way, how many years? 89, 2000, yeah, 25 years later, we clarified it. We clarified it for everybody to see what the differences are. Okay, so we have what's the difference? Conceptual difference. Clark's procedure, original procedure, routes through a linear reservoir, as he intended to do, a discrete time area derived unit hydrograph. Discrete time area derived unit hydrograph. So he took the hydrograph and routed. We didn't do that. Ponce's procedure routes a continuous time area derived unit hydrograph. In other words, we derived a unit hydrograph. He did not route a unit hydrograph. He routed a discrete unit runoff, not unit hydrograph. Time area derived unit runoff. So there's a slight difference in there because the first one is a hydrograph. The second one is a hydrograph. What's the difference between a hydrograph and a hydrograph? Well, given the time of concentration in there, the hydrograph is going to start at 0 and end at 0. The discharge, it's going to be a discharge. The hydrograph is also a discharge, but it does not start at 0 and end at 0. It starts in a finite value and it ends in a finite value. And we will see the shapes later on, and you will be able to grasp graphically what I mean. Since the unit hydrograph has a longer time base than the unit runoff hydrograph, Ponce's procedure provides a longer time lag and a correspondingly smaller peak discharge, obviously, because the mass has to be conserved. If the time lag is a little longer, then the peak is going to be a little smaller. You understand the time, the volume of the hydrograph has to be conserved, and it is conserved. All these methods are mass conservative. The difference is not substantial. As expected, both methods are shown to be 100% mass conservative. Okay, so I'm going to be going here through a little bit of background because I know many of you lack the background. The HMS Clark unit hydrograph requires a specification of a watershed basin drainage area, etc. We already covered this ground. Let's speak a little bit here about HMS. HMS was originated in released, the first release of HMS that stands for Hydrologic Modeling System was 1998, dated 1998. Prior to that, the predecessor to HMS was HEC1. HEC1 dates back to 1968. So the Corps worked with HEC1 for 30 years. And what's the difference? The HEC1 is a character cell model, meaning driven by data, digital data. And in the old times, you used to work, the input was worked with cards, with computer cards. Eventually, the computer cards went the way of the wayside, and we got into CRTs, and then what you have right now, directly on the flat screen and typing the stuff directly. You don't see anything physical, any physical input like it used to be in the past. So obviously, that was an improvement. Everybody says it was an improvement. 1998. It took the Corps, though, 30 years to get from character cell to GUI. 1998. I happen to know because in 1995, when I decided to do the second edition, when I started on the second edition of my book, which now you see online, there was a chapter in there on the practices of the federal agencies. So I went over to Davis to talk to Arlen Feldman, who was the head of research over there. And he was my acquaintance, my friend, to find out what was the plan, 1995, 1996. What was the Corps' plan regarding HEC1? I think that was a valid question for somebody like me that was writing a book, okay? Because if they told me they're gonna junk HEC1, drop it, then I wouldn't have to pursue it anymore. Why should I pursue something that the Corps is not pursuing, right? So then I got the answer from him. He said, Ponce, we're working on the replacement of HEC1. So my advice is don't touch it. It's gonna be old in a couple of years. And sure enough, in a couple of years, the HMS was released and the HEC1 was dead on the water, okay? Which obviously prompted me to do there's several things with my book, which I haven't done yet, by the way. My second issue, that is second edition online of my book, which is, by the way, free and in color, unlike the first one, which was not free and was not in color. It was not online, it was in print form. Still has to have a chapter 13 to finish. And to be honest with you, I'm confessing to you at this point that I don't think I'm going to do it. It's a book that will have 14 chapters instead of 15 chapters. At any rate, there's a lot of reasons for that, but I'm not going to dwell into that at this point. The point is that HEC1 was dead in 1998, dead on the water, and HMS came about. But HMS still does have the Clark methodology. And the Clark methodology is based on, as you know now, on a histogram. But the Corps came about a generic histogram, which is this one over here. And that's what they use. They figured that was good for them, and if it was good for them, it should be good for everybody else. And that is kind of a fact, because when the Corps puts something out for their practice, everybody in the world, in the United States, let alone in the world, uses it. There's very little wrestling as to what the Corps does and what they don't do. There could be disagreements, but in general, the practitioners don't oppose it. Okay, so we have in here, and this is the HEX default time area histogram that we had calculated based on their equations. This is the equation here over here. The equation 1 is the default time area histogram of the Army Corps. How could you have a default time area histogram when in fact the Clark method is supposed to take account of the shape of of the basin, the graphical or geometrical shape of the basin. Don't ask me that question. They have a default, and this is a default, and this is what we're going to use. This is what the area histogram is, like an ovoid shape basin. I already told you that the ovoid shaped basin may be generic, may be nice looking, but it's not all of them. There's a few of them. I would say in my practice, I've seen maybe 20% of them that are not ovoid. They're very much different from ovoid. So, but you could, I believe, in here, put anything you want. If you don't have a value to put in there, then you can put in the shape that they recommended. Routing principle, we already covered this ground extensively: convection and diffusion, translation and concentration, diffusion, attenuation, and storage. There are three types of physical features: reservoirs, stream channels, and watersheds. Reservoirs is my chapter 8 in my book. You can refer to it. You know where the link is. Stream channels, chapter 9, and watershed basins, chapter 10. Okay. With respect to convection and diffusion, the situation is different for the three physical characterizations. We all know what a reservoir is. We know what a channel is, and we also know what a watershed basin is. The reservoir is a point. It's really flow at a point. It's not even one-dimensional. It's zero dimension. The stream channel is a one-dimensional process. Well, it could be two dimensions, but we're considering here is a one-dimensional only. That was the beginning of it. We've only had 20 years, exactly 20 years of practical applications in 2 dimensions. And I know for a fact that the Army Corps is working on the 3 dimensions, but I don't think they released it. They are about to release it. The 3-dimensional model in HECRAS, not HMS, HECRAS. But they're still in 2 dimensions, and we're talking about here 1 dimension. So we have reservoir, 0 dimensions. Stream channels, 1 dimensions. And watershed basins, 2 dimensions. Yes, watershed basins in 2 dimensions. 2 dimensions, yes, 2 dimensions. Why not say it? However, the watershed basins can be lumped or distributed. And the methods that we're covering right now in this section are lumped, meaning only 1 answer. That's the difference between lumped and distributed. In a basin, and if you're doing a distributed calculation, you can get the discharge at any point inside the basin. While if you're doing a lump calculation, you can only get 1 value at the bottom, at the downstream end, at the delivery, at the mouth of the basin. So that's the difference between lumped and distributed. In here, we're talking about lumped method. The Clark method is lumped, okay? So and also we know, this is reiterating, that the time area method provides only convection. That was identified clearly by Clark at his time in 1945. Let's also kind of dwell on this or drum this thing in, that the issue of convection and diffusion, the issue of convection had already been identified in 1889 by Kuchling, who purportedly developed the rational method. Although there are references in the literature that say that Kuchling didn't do it, and there was Mulvaney and others that 20, 30 years later did it. So far, the issue of credit on the side, Kuchling is widely considered, 1889. So since 1889, we have had a rational way of calculating convection, but not diffusion. So then in 1945, when Clark applied the time area method to, I'm sorry, that's right, when Clark applied the time area method for a large watershed, which was not considered a small watershed, was already in the range of thousands or hundreds of thousands of square miles, then he decided to add the diffusion. He says, I can't operate this unless I put some diffusion. How much diffusion? Well, I'm going to run a linear reservoir through it. And what is the K? The K, I can find it by some gimmick, which is not actually gimmick. It's a procedure. If you have data, you can find the K. If you don't have data, then you can guess the K based on experience from prior situations, which, by the way, that's called regionalization in hydrology, regional hydrology. It's done all the time. Again, if you have data, go and use the data. If you don't have data, go use data from neighboring watersheds or neighboring or similar situations. And it can be done, and it's been done. Formulas for doing precisely this are given in various books. Like I said, my friend Vijay Singh has several books in hydrology, and one of the books he's talking about 5 or 6 formulas for regionalization of the K constant with mind to apply it to the Clark method right here. Okay, so then we have the time area method, and we have already seen that, so I'm not going to dwell on it. We have an example, a clear example of how this is done. And then we're going to apply it to a rainfall, effective rainfall, which is over here. Effective rainfall hydrograph. And we have the time area method of watershed routing. And I already covered this, so we're going to go quite quickly through this. In the red here, we have the histogram, our classical histogram, right? In the blue on top, horizontally, we have the effective rainfall. And the time area histogram proceeds like this. It's kind of a convolution. It's actually called convolution. Yes, yeah. Convolution is a procedure in mathematics, which does precisely this. It takes several impulses and multiplies them times, well, impulses on one side and impulses on the other. The 2 impulses, 2 hydrographs in here. 2 hydrographs, one over here and one over here. You can see they're blocks. So they produce, given the right time considerations, they produce a hydrograph. They produce a hydrograph over here. Can you see they produce a hydrograph? But this hydrograph has no diffusion. It has no diffusion. And the way we have calculated this for clarity is that we used kilometer square centimeter per hour, which gives you discharge, as you know, because it's an area times an intensity, and the area times an intensity always gives you a discharge, because the area is L squared, intensity is L over T times L squared, L cube over T, and that's a discharge, L cube over T. So then we converted that by multiplying by the appropriate factor, which is 2.67, to the outflow in cubic meters per second. We did this because we wanted to show that this was a mass conservative method. And the only quick way that we had to do that is to sum up column 9 and get a number there, 650, and then also demonstrate that the addition of the blues was 6.5 times the kilometer square, which was 100, is 650. 6.5 times 100 is 650. So we have proven that, in fact, this method is 100% mass conservative. And then we proceed to multiply it times 2.67 in order to get the answer to this problem. Okay, and we explain in here how this is done. So if I went too fast, you can always go back to the reading in there. As I say in there, the total rainfall is 6.5, the watershed area is 100 square kilometers. Thus, the total rainfall volume is 100 times 6.5, 650 kilometers square centimeters, which is exactly what we have in here. Okay. Okay, a complete rainfall runoff transform model using the time area method and adding diffusion consists in 2 steps. Use of the time area method to provide pure convection and generating a translated only hydrograph. We already done that. That's the previous table. And then routing the translated only hydrograph through a linear reservoir with an appropriate storage constant. That needs to be qualified. Appropriate storage constant. It cannot just be any storage constant. If you have any storage constant in there, then you're just going to route and get some diffusion, but it's not going to be the right amount of diffusion. So you have to know how to do this with the appropriate storage constant. Like I already told you, there's 2. One measured and the other one obtained from regional analysis. And then we go into the linear reservoir routing, which we have not been here before because many of you, or some of you, I'm not going to say anything there, have not taken this course yet, because this is not really taught it in hydraulics, nor you have to take hydrology in order to learn this stuff. Linear reservoir routing. So the linear reservoir is a computational procedure that provides diffusion to an inflow hydrograph. Absolutely correct. In other words, a hydrograph routed through a linear reservoir effectively diffuses, that is, it lowers its peak flow while it increases its time base. The amount of diffusion depends on the value of the storage constant K relative to the time interval delta T. There's always a time interval in these situations. Values of delta T over K less than 2 provide diffusion. The lesser the delta T over K, the greater the diffusion. We are going to be explaining this in a better way, or no, in a clearer way later on. Let's just take it at this point. Maybe too much too soon, but that's so be it. Okay, values of delta T over K greater than 2 provide negative diffusion, meaning you can't use it. Because delta 2 over K greater than 2 means that the K is too small. And the K cannot be too small because it would not be a reservoir. It has to be a certain amount for it to store. That's why it blows up. It could blow up in your face, by the way. It could really wild answers, negative answers. Hooks, or so some wild things happening. Exactly why is this thing happening in numerical analysis? The answer is it happens all the time. You got to be careful. Not everybody can do modeling, particularly numerical modeling. It's very sophisticated way of doing it. By the way, I have a bug in there. I'm going to write it down here. I have a period where there should be a comma. Okay. Given inflow, outflow, these are the formulas. This is standard stuff. This stuff is about 80, 90 years old. It was developed in the mid-30s. These formulas in here, well-known formulas. So now we route the time area through a linear reservoir. So which time area? Let's look in here. Look in here in column 9, it says 0, 5, 25, 60, 115, right? That's column 9. That's the outflow in kilometers square. Here we go. So we put that column 9 on the previous table. We put it as column 2 on this table. Can you see that? Exactly. And now we are going to route through the linear reservoir. And for that, we need to figure out what the routing coefficients are. In this case, the routing coefficients defined by these formulas over here. These are CO2, C0, C1, C2, right? C0, C1, C2. And over here, we have the C0, C1, C2. We calculate that based on the storage constant given, and we get C0, 0.2, C1, 0.2, C2, 0.6. The three coefficients have to add up to 1, which they do. 0.2 plus 0.2 plus 0.6 is 1. And then we proceed to do the routing computation, normal routing computation. Like I told you, these procedures date back to 1930s, 1940s. I would say 1930s, definitely. Okay. It was at about that time, how interesting, that the interest was rising in terms of computations, because technology was moving ahead. We still could not do a whole lot because there was no digital computer at that time, but people spend their lives doing the hand calculations. You can do this hand calculation, I would say, for a simple example, it would take you maybe a couple hours. If you're good, it will take you an hour. Of course, if you did this on a computer, programmed a computer, it will take the computer a fraction of a second to do it, like 0.01 second. We know that for a fact. We've done it hundreds of times. Okay. And these calculations obviously were done on the computer also. And they were reproduced here for your information. Okay, so then we have the outflow from the linear reservoir. So let's compare columns 2 with column 6. Whereas 25 in column 2 is 6.6 in column 6. Whereas 60, it's 20. It means it diffused. It's diffusing. It's so diffusing that this inflow hydrograph ends at 0 sharply. Can you see that? 20, 0. It drops from 9, 20, at 10 is 0. It dropped completely because it is a hydrograph that lacks diffusion. It was generated only with the time area histogram. But if you run it through the reservoir, then your reservoir lingers out, you know, and it takes 26 hours to go back to 0, slowly but surely. It goes back. These methods always go back to 0, given enough time in the tail. In this case, we ran it all the way to 26 to show that, in fact, it does go back to 0. And lo and behold, if we add the the numbers in this column number 6, they add to 650, prove that this thing is 100% mass conservative, even when it is not a line, but a curve. It's a curve, definitely a curve. It has a curvature in there, and yet it gets to 650. How is it that it could be so perfect? It is perfect. I'm really amazed. I was amazed a long time ago. I'm not amazed anymore. This thing works all the time. That's the way it works. If it were to lose mass, it would be wrong. How much? Well, this kind of procedure, since it's relatively simple, not that many calculations. There may be a couple 100, 300 calculations here. That's nothing. Okay. The real models, the ones that are run extensively, do millions of calculations. Okay. So 650 here is as expected, and it was good. And then we multiplied times this 2.67, I believe, or 2.67, and we get the outflow in cubic meters per second. Okay. Note that the peak flow has decreased to 145. From 145, which is over here, 145, right in here, right in there, 145, that's the peak flow, to 109. Not only has it reduced to 109, but the 109 is one step later, from 6, 145, and 7, 109. Why? Because it has to be that way, because there's spreading of the hydrograph. So the peak is not going to be at the same time. It'll be a little bit later, maybe 1 or 2 steps later. In this case, it's only 1. Not a whole lot of diffusion. Okay, so this is it. We have a plot of the time area histogram, or rather time area hydrograph, and the time area hydrograph routed through a linear reservoir. Okay, that's it. It's clear. Now we go here into unit hydrograph concepts. I asked Nicole Nuccitelli to write the whole thing as if it were a book, because one of the specialties is to explain on the web online everything clearly, so you don't have to go back out there and do a lot of research in order to get to the truth. So this explains various things that could be considered a reiteration if you were publishing this paper for a journal. If you were trying to do it in a journal, the reviewers would say, goes to the reviewers, 3 reviewers. The reviewer would say, you know what, Professor Ponce, this unit hydrograph concept, we don't like it, drop it, because we already know it. It's been around for 50 years. Sherman, 1932. So that's 90 years, right? But in this case, we're not publishing. We're publishing directly on the web. So therefore, we don't have that problem. We don't have to ask anybody permission to write this thing. Right or wrong, that's the way it's done on the web, okay? That's good and bad at the same time. Hopefully, in our case, only good. Okay, so unit hydrograph concept is used in flood hydrology as a means to develop the hydrograph for a given effective storm. This is almost straight coming out of our book. The word unit is normally taken to refer to a unit depth. However, the word unit also refers to a unit depth of effective rainfall lasting a unit duration. So we really don't know whether the word unit refers to unit depth or unit duration. In fact, I think it's more refers to unit duration, but it's gotten very confusing with the unit depth. Really, it's an indivisible increment. That's what the unit refers to. Typical unit hydrograph durations are 1, 2, 3, 6, 12, 24 hours, depending on the size of the watershed or basin. Okay, 1 to 6 hours are common. How interesting that the unit hydrograph should have been developed by Sherman. Well, that's what they say, although Marcus in his interview with me said that he didn't. And it is true, though. Sherman got the credit. He was at the right time at the right place, and he was lucky that he got the credit. But there's a couple people, I don't mention names, I don't remember, that had written about it a couple or 2 years earlier. I think in 1928, actually, is the date of this publication in the Boston Society. So Sherman picked it up, or he developed it independently. We don't know. I would have to go back to the original paper by Sherman and see if he did quote the other gentleman from the Boston Society. I don't have the time to do that. All I can say is that at this point that Sherman is given the credit for coming up with the concept of the unit hydrograph. What is it? The unit hydrograph is a marvelous, magnificent way of accounting for diffusion. Let me repeat that. It's a magnificent way, it's easy, understandable way of accounting for diffusion. It gives you a way of saying, for this particular block of rain, that's going to be the response. And therefore, since this is the response, I can assume linearity, quote unquote, and run this as if it were linearly and develop the hydrograph for the complete storm, not just the unit storm. So the unit storm is going to serve as a basis, almost like saying, I'm going to build a house and I'm going to do it out of bricks. First, let me get the type of brick and the size of the brick and the color of the brick. And then I'll build the whole house. That's exactly the way he did it. He developed the brick, the unit hydrograph, the brick meaning in a assumed fashion, right? It's not the brick, it is a hydrograph. It's a unit hydrograph. Remember, when we build a house, the house or the walls are built out of unit bricks. They're bricks that are units, right? Same thing in here, okay? Why did he do that? Because he realized at the time what Clark also realized. But the difference was that Sherman was working in 1932 or a little bit earlier, because he published it in 1932. And Clark was in 1944, 45. So Clark was a little later. But they were working on the same problems. They had the same problems. The problem was how to figure out the flood of a large watershed, because they knew at the time that they could not use a rational method. They perhaps didn't want to or could not use the Krieger method, because the Krieger method could have solved their problem. I wasn't there, as I say, and I have no way of telling you why they didn't use Krieger. My sense is that they felt that Krieger was too crude of an answer, which it was, by the way. And therefore they said, we're going to do something better here. It's about time that we get a little fancier with the hydrology. The Krieger is good, but is good only in a limited way. So both of these gentlemen, both Sherman and Clark, developed ways of proceeding beyond what Krieger had done. That's fascinating, isn't it? Okay. So basically, Krieger had said that the curve is going to come down because of diffusion, although he didn't call it diffusion. And these other two gentlemen were going to say the same. They're going to say the same. The only difference is that Sherman did it by creating the concept of unit hydrograph, while Clark did it by running the time area method without diffusion and then running it through a linear reservoir. It's a kind of a two-step process, but it's still a process to convect and then to diffuse. Because the convection was not the problem. The problem was the diffusion. And Sherman identified that and created his unit hydrograph because it's the element to create diffusion, right? Clark didn't do it that way. He recognized the convection was important, but he said, well, I need to add something in there. I'm going to add the diffusion through a linear reservoir, which K I'm going to calculate. And that's the way they did it. To this day, we use Sherman and we use Clark, and they don't see I, meaning they are different methods. You could apply for a base in Sherman and you can apply Clark. As a matter of fact, Sherman has variants, has 3 or 4 variants. So you can apply, as a matter of fact, I already talked about that in this class, the various ways of creating unit hydrographs. Okay, so I'm not going to dwell on that more at this point. What is a unit hydrograph? The Clark original unit hydrograph. We went all the way to Clark, and I believe if you're interested, you can click over here and our system will load you into Clark's method. And notice this little bar in here? That shows that this PDF is huge. It's about 40 pages, 1419. 1419. And the last page is 1488. Exactly. So 19 from 88 is how many? 15, 50, 68. 68 pages. 68 pages is the article by Clark. And it's there for you to see. So if you're curious, go in there. Be my guest. See what you can find. Okay? But you don't have to, because we already done it. We dissected it, digested everything. Okay, the drainage area. He used an example, the Appomattox River at Petersburg, Virginia. These examples are the examples of Clark. This graph over here is Clark's. We kind of reproduced it to put it in here. It was that important. This is a reproduction. It's not just a Xerox of what he did. It's a reproduction of his work. And we have the computation of the Clark method, okay, and in detail, taken from the work of Clark, and we have it over here. Can you believe all this work? It's amazing. This is Nicole's, by the way, because she produced the HTML. We teach our students to work with HTML because we believe that they better learn it, and the best way to learn it is at school, right? So she worked with the HTML. She learned. It's no big deal. I think anybody that considers himself or herself a grad student can learn HTML in a week. There's only 20 commands. How long would it take for you to learn 20 commands? 22 commands, of which only 5 are really the ones that are used. The others are not used as often as the first 5. So it's a very simple tool. Unfortunately, it has been mystified in practice, meaning it has been made difficult when in fact it isn't. Okay, so this is what we did over there, and we reproduced in HTML the calculations of Clark. Calculation of Clark's original for the case delta T, and we have in here. Now we're going to do table 5 illustrates a more general computation. Now we're going to deviate from Clark. We're going to apply our own method, which is over here. This is our own method. As you can see, the numbers in there are our own, 10, 30, 20, 40. We're already familiar because we use that for the time area method. Okay, so the time area method was just this, but now we are going to do a more general computation where the time interval is not equal to the unit hydrograph duration. In the case of Clark's method, he did it the same, delta T equal to T sub R. But we felt that the more general method is when delta T is not equal to T sub R, because if it's not equal to T sub R, then the method gets a little bit more complex. And we decided we were going to explain how to do that. It's easy to do the delta T equal T sub R. It is more complicated to do delta T not equal to T sub R. So we show an example here of delta T not equal to T sub R. Delta T is 1 hour. I'm sorry, in here, delta T sub R is 2 hours. T sub R is the duration of the unit hydrograph, 2 hours. That's a fundamental parameter, duration of the unit hydrograph, the physical parameter. While delta T is the numerical parameter that we've chosen to do the computation. And if they're not the same, then you got to do this table. As you can see, 1 centimeter in 2 hours is 0.5 centimeters per hour. That's in the blue in there. We have to discretize, and you get to separate it and then do the computation accordingly, the time area method accordingly. So we come in here, this 1/2 is 5, 15, 10, and 20. And this one is also 5, 15, 10, and 20, but it is lagged. It is lagged. So we have the sum, the discrete unit runoff hydrograph. This is it. Okay. Then we run it through a linear reservoir and we get the outflow. We run it through a linear reservoir over here and get the outflow. Well, I don't have to repeat that. We already done it. So you can see that over here you have 5, 20, 25, 30, 20. The peak is 30, right? And over here, the peak is 21. Compare column 5, which is without diffusion, which is abrupt. It starts abruptly in here. These are blocks of something. It's actually a block, a hydrograph expressed as a block. Hydrograph, it's not a hydrograph. That's the difference, the key difference, because it starts at number finite and ends at finite number. Once we route it to the hydrograph, okay, then we start at 0 because it starts at 0. That's a hydrograph. And it ends at 0 too. Can you see that? In column 20, line 22, 0.004, we carry it all the way to 0.004, but it is obvious that in 2 more steps, this will reduce to 0.000. I should have actually done that, but I didn't do it. Okay, so that's the partial outflows, the outflow from the linear reservoir in kilometers square centimeter per hour, and then we multiply it at 2.67 in order to get the outflow in cubic meters per second, which is the answer of the problem. In table 5, the discrete unit runoff is highlighted in cyan, right? Background, in cyan background. Okay. Note that Clark's original methodology conserves mass exactly, right? In this case, it's 100 because it's not 650, it's 100 at this point, right? In effect, the sum of columns 2 is 100, and the columns in the effective rainfall volume is 100, and the sum of the hydrograph ordinates is 102. So it's mass conservative. And now Ponce's Clark unit hydrograph. Ponce's Clark differs slightly. Ponce applied the time area method to a given unit rainfall to obtain a continuous unit hydrograph based on the time area histogram. He then routed this hydrograph through a linear reservoir to obtain the Clark unit hydrograph. Ponce's Clark retains the essence of the original methodology while providing an improved unit hydrograph consistent with established routing principles. Okay, so we have in here like this or here. Okay, so what's the difference between the cyan and the magenta? The cyan starts abruptly, 5, 20, 25, 30, 20. The other one is 5, 20, 25, 20, 30. But this one does not start or end abruptly. It starts at 0. It is indeed a hydrograph, not a hydrograph. This hydrograph is the one that we're going to route, like normally anybody would route and get to the right answer. So the issue then is as far as the answers are concerned, this one's going to be a little more spread. So this one's going to be 58. 5847 is the largest number. That's the peak. Well, over here we have 5919. That's right. 5919 in step 4. Well, over here we have 5847 in step 5. So it's a little reduced in one lag. So the time lag, which is a fundamental parameter of the unit hydrograph, is one more to the right. Okay, magenta color. So we have in here Clark and Ponce's side by side. And then we have the plots side by side. Good, very good. That's it. That's the answer to this question or problem or story. And then we generated the online Clark. Enables the calculation side-by-side comparison of Clark's original and Ponce unit hydrograph. She did that too, by the way. I helped her out because, I mean, once you get to PHP, that's not a week job learning. That's more like 6 months. So I helped her out. We did it together. We've done literally hundreds of these models starting in the year 2005. And we have continued to do it over the years. Now, actually, we ran out of ideas now. With more than 300 calculations, we basically have calculated everything that we could calculate. As a matter of fact, last student that graduated with us a couple of years ago, right after the pandemic, her name is Jana. Jana was charged by me to convert a Fortran model of groundwater, a Fortran model of groundwater flow that we had for 20 years, which was a very conceptual, fundamental groundwater flow model, basic for teaching purposes. And I basically told her, you put it in PHP, and that's what we're going to do. That's what you're going to do as a thesis. Convert it to PHP was not an easy matter. It took her a year to do that work. Because first you got to understand all the math and all the numerical analysis and so forth. So she did the work, but I got a little sad story to tell you. Not a sad story. We knew that was going to happen. That at the end, the Fortran program ran in about 3 seconds, and the PHP program took about 5 minutes to run. Let me repeat. The Fortran program ran with the speed of light, and the PHP 5 minutes. So that is a detriment, of course. We did it because it had to be done. We knew that was going to happen because we have experience with this. Why is that? That the PHP program developed in the year 2000 and the Fortran program being developed in the year 1955 is a preeminent, not preeminent. The original, not the original, is the first advanced language or not machine language, but advanced language computer program, 1955, Fortran, 54, 55. And 45 years later, computer scientists developed the PHP, and it's, like I already told you, it's 100 times slower, more than 100. Why is that? There's a simple matter for this issue. The Fortran programming, all it does is floating point calculation, which is what computers of that time, 1955, that is all they did. Only engineers and scientists were using the computer at the time, and they were using it to run calculations, modeling, physics, mechanics, 1955. In the year 2000, 2010, the situation has totally changed. Now the computer programs are required to do everything, not just floating point. Everything means just about everything. I submit, without having done any calculations, that I would say 99% of the CPUs around the world are being used to chat on Facebook or WhatsApp. That is true. So the computers are being used for totally something different than what they were used in the beginning. I have the privilege to have used the IBM 1130 in the year 1967 for the first time. I mean, Ponce for the first time. I was not the first one that used the computer. It was an IBM 1130, which is 7K of memory. The current computer that we are running with now, the one that I'm talking to you right now, is have 32 gigabytes. K, mega, and giga, right? So that's about 1 million times capacity. That's storage, not RAM. RAM is even, I don't even want to consider. I have not thought about that. So at any rate, that's a story on the issues of Fortran, vis-a-vis all the other models that have come out, rather languages that have come out. They have had to diversify, and they did it because it was a commercial thing to do. I'm not negating the fact that they needed to do it. I'm just saying that is the way it happened. Okay, so that's the outflow calculation. I'm not gonna run the model at this point because we're running out of time here, but you can run the model, okay? You can run the model that we have created with is this one over here, online routing Clark, okay? You can run them, I already did it and it works, so it's fine. So I'm going to briefly talk about the evolution of Clark's unit hydrograph. Oh no, wait a second, I missed this one. Comparison between Clark's original Clark's and Clark Ponce. Now, about came Andrea Scott, who is a student that some of you may recognize by name and even by in person. Andrea has just graduated with a MS in our department. And she wrote a couple of papers with me because she did the work and it was good work. And one thing led to another. And I invited her to rewrite the paper and put it on my site. Because, you know, the paper needs to be improved in order to show it, to prove it on the site. It's not enough just to do work like the works that you guys are doing. It has to be uplifted a little bit or a lot to put it on the web. Typically, it's only a little bit, because if a lot, I'm not going to do it. Okay, so Andrea Scott wrote this thing. The idea was that she was going to reiterate or regurgitate that what Nicole had done in a slightly better way, covering a lot more ground, because that was a new thing. So she covers the methodology, okay? And I'm urging you to look at this paper because it's a good paper. Computer hydrographs is the correct number, Clark method, the same thing we're talking about here. Online routing Clark and online routing Clark 2 were used in the analysis. I asked her to do this. I said, we have run 10, 20, 30, 40. You run different histograms and see what happens. That had not been done by Nuccitelli. Nuccitelli's job was just to show the goodness of the comparison, actually, between Clark original and Clark Ponce, okay? But Andrea did the variation of the hydrographs. So 10, 20, 30, 40, that's our standard, but 5, 15, 25, 60, that's kind of peaked toward the end, 60 in the front, and so on and so forth. You see our objective here. We wanted to see the variability of the results as we changed the scenarios for the histograms. And this is what we came about, and we graphed them. Scenario 2, scenario 3, you can see in here how it varies. Scenario 4, so we basically cover all grounds in terms of the possible scenarios. Scenario 6, no, scenario 1. No, this is for C2. Let me see what I got. Table 1, scenario 5. There's a bug in there. I have to change that. There's a comparison between Clark's and Clark Ponce unit hydrograph. Clark Ponce unit hydrographs. Clark's original scenario. Figure 6A, 6B. Oh, okay. This is for different C's. C is the Courant number. That is the delta T over K. Courant number 0.8 and then Courant number 0.4. I'm going to talk more extensively about the Courant number later on in the next publication. By the way, the issue of Courant is an interesting issue that we need to explain in here. Courant, who is Courant? Courant was a gentleman originated, I believe, in Germany, who in 1928 wrote a great paper on the numerical analysis. He was one of the first ones to identify the issue of a number, a controlling number in the computations. If the number was not followed correctly, the laws of Courant were not followed, you were going to get garbage out of the computation. And since you didn't want to do that, you had to follow the Courant laws. So that led to Courant criteria and then to Courant number. Now, I believe that I could be wrong on this, but I believe that we introduced the name Courant number. There was Courant law, Courant criteria, Courant this, Courant that. We call it Courant number because there's a whole lot of numbers out there that we use. And why not use the name Courant for the Courant number, which is exactly what it is, the Courant number. So we call it Courant number. I say this because the Army Corps had not done it. The Army Corps had called it delta T over K, which is what we call the Courant number. And they kept repeating delta T over K, delta. They didn't want to, or they could not. They just didn't know at the time that this was indeed the Courant number, and they could be called the Courant number. In their defense, they were doing this work in 1950s. In 1950s, it was just the beginning of the thing, so I'm not blaming them for not doing that. As a matter of fact, the gentleman that introduced this whole thing was a guy that was a developer of the SAR model, whom I actually met in person in his retirement maybe 30, 40 years ago. He precedes me a generation. I don't remember his name right now. Great guy. He put the delta T over K into the model in there, but he failed or would not or could not call it Courant number, which we did in our book. We introduced the concept of Courant number in our book in 1989. And this C that you see in there, right in there, is the Courant number. Okay, Courant number is 0.2 and so on and so forth. So as you can see, we're doing a lot more analysis here than Nuccitelli ever did. Nuccitelli was doing a show basically because it was the beginning, the first. You cannot do too much. So she did the demonstration of the concept, and then Scott did the testing. So we got the graphs in here, as you can see, all kinds of variations in the summary of the theoretical basis for Clark's original and Clark Ponce's methods are explained and compared. The effect of the unit hydrograph off, but this should be on. I think we made a mistake in here. Well, whatever it is, I can fix that. The effect of the unit hydrograph on catchment shade, Courant number, and catchment area is elucidated. It is shown that Ponce's method consistently provides a somewhat lower time base and a correspondingly smaller peak discharge than Clark's original methodology. This is a direct consequence of Ponce's use of a continuous time area derived unit hydrograph in lieu of the discrete hydrograph used by Clark. No question in our minds, there is a difference in there. As to which one is better, I mean, of course, I developed a method. I felt it was necessary. So I have a bias towards my method. But I would definitely say that whoever wants to continue to use the Clark method, go ahead, be my guest. There's not that much difference. There may be 5% difference. In some places, there's no difference. Look at this. Over here, there's hardly any difference at all. So the chances are that the difference are going to be maybe 5%. And who cares? In hydrology, really, who cares if the difference is only 5%? If the difference gets to be more than 20%, I would start to worry about it, but not 5%. So direct consequences of Ponce using the continuous in lieu of the discrete. The differences are consistent with the methodologies used and do not appear to be significant. That is the conclusion now. I got 9 minutes and I'm going to briefly, not talk about it, I'm briefly going to show you. It's a show. It's a, my advisor used to use the word dog and pony. I don't know what exact connotation does that have. I think it has a bad connotation. It's like a show. It's a show. So we're going to do a show in here. A show of what? of the paper that in 1998, the two people that were in charge over at Army Corps of Engineers Davis, these guys are hydraulic engineer, U.S. Army Corps of Engineers Davis. And this is his boss, Research Division Chief, U.S. Army Corps of Engineers Hydrologic Engineering Center, Davis. These two gentlemen in 1998 wrote this paper. This is 1998, June 1998. As they prepared to release the HMS model, 1998, they wrote this paper. I'm sure they wrote the paper a year before that, because anything you want to publish, it has to be done before with a year in anticipation. But in 1998, I positively know that the model was released, and it was the time that this thing came up. June, no. June 1998. Oh, wait a minute. Yeah, January. This was in January. Okay. So they heard it, they put it out. Why would they spend the time on this? And by the way, this has the signature of Arlen Feldman in there, who was at the time and for many years until he retired, head of research at Heck Davis, head of research. Big guy, capable guy. And they did this work, evolution of Clark's unit graph method to spatially distributed runoff. Clark called it unit graph. He didn't call it unit hydrograph. And because it was kind of not a unit hydrograph, it was a unit graph, that's right. And therefore they kept the method. What is the summary of this method? Well, we have time in here to at least look at the abstract, which is probably what we're gonna finish. In 1945, C.O. Clark proposed a method to develop synthetic unit hydrographs for the modeling of watershed rainfall response. That is correct. His technique utilizes two components, a translation hydrograph and a linear reservoir routing. Correct. Clark's three parameters, the time of concentration. The time of concentration is the total length of the hydrograph. A storage attenuation coefficient, which they call R in here. And a time area histogram, right? The time area histogram gives you the distribution in time of the responses. Can be estimated for gauge basins. So you must have those three: the time of concentration, the histogram, and the R, which they call it R. We like to call it K. For ungaged basins, T sub C and R are difficult to estimate. T sub C can be approximated by analyzing physical basin characteristics, whereas both T sub C and R have been successfully estimating using parameter regionalization. I already said that. That was in the book of my friend Vijay Singh, my colleague and friend Vijay Singh. Vijay and I went to school together, by the way, at Colorado State in the middle 70s. So everything that we say in here so far is the truth, okay? Technologies for observing and managing spatially distributed watershed and rainfall information are constantly evolving. That is the truth. Why? Because it was at about that time that GIS was coming of age. The first time I heard about GIS like that, Geographic Information Systems, or Geographic Information System, was in 1987 when I went to Maryland. There was a conference in Maryland, and some guy out there that I don't remember who he was or at that time said, Ponce, we're looking at GIS. I said, what? I never heard of GIS, 1987. I'm telling you this story because, so you to see the frame of reference in here. GIS came about in the middle 70s, no, middle 80s. I don't know exactly where, but then eventually it evolved. So by that time in the mid 90s, at end of 90s, it was all over the place. And it's still, and it is good. It's a good method. It's a good tool. It took over in 10 years and now it's taken over completely. It has taken over so much that I have a little bit of point of a criticism. They have actually foregone many of the methods, many of the original methods. They established a new hydrology on top of it, like burying it under. And this paper here is a proof that I am not too far from the truth, because what they're going to do in here is fiddle with the Clark method in order to accommodate it to GIS. Isn't that fascinating? It is. For me, it is fascinating. Okay, that's exactly what they're doing. They're accommodating it. They're taking an old method and trying to make it work with the new methodology, which is GIS. Okay, the improved availability of aerially oriented data, that's GIS, brings the challenge of integration of these data into hydrologic models. It is a challenge, and it still remains a challenge, by the way. The Hydrologic Engineering Center, HEC, has developed the program Mod Clark to take a first step in this integration. That is really amazing for me that they should actually put this in black and white, because they took the first step and they never bothered, or I guess they couldn't. They didn't have the wherewithal to take the second step. And this has been 20 years already on this. We're still in the practice of the first step, right? But it was the first step. So they were correct. They're not saying anything wrong. I'm just saying, oh, so Mark Clark is based conceptually on Clark's 50-year-old methodology, 50-year-old up to time. Now it's 70 years old. It uses next generation weather radar, next rad data. That's cool. That is the modern data which was becoming available at the time. So really the challenge is to integrate, as they try to do in here, to integrate the methodologies of old, like Clark, with the techniques of new, which is the GIS and the radar and all this other electronic stuff, which should be pursued because it's progress. Ability of Clark's technique to accommodate the spatially distributed nature of rainfall and runoff illustrate the adaptability of Clark's original methodology. I'm not going to make any comment on this. The only thing I'm going to say is this, which is correct, which they didn't say though. Okay, they finalized with the demonstration on this adapted methodology. What I'm going to say is not a criticism, it's just a statement of fact, is that these people had a choice. These people meaning Daniel Call and his boss, Arlen Feldman. Basically, Daniel Call. He's the guy that wrote the paper, and he was responsible. He had a choice. His choice was go with a lumped method, which was going to be relatively easy and preserve the convection diffusion nature of the problem, more or less in the ballpark, okay? Or go with a distributed method, such as the kinematic wave, to do it in a quote unquote better way. But they decided, in their wisdom, as they say, not to go on the second route because it was going to be a can of worms that they're never going to finish, and it's got its own drawbacks, right? So the issue here is a very simple issue, actually. Go simple and try to do the best you can with a simple method, keeping in mind the KISS principle, which I already reiterated to you many times, or go complex, full-blown, everything, get all your guns out there and shoot. You don't know who you're going to kill, meaning, I mean, what could happen? We don't know what's going to happen. At least the Clark method was somewhat predictable, stretching it, but it was somewhat predictable. So they went with the first route, easy, KISS principle. We're going to do Clark. We like Clark anyway. We are Army Corps. We've been using Clark for 40 years. We don't want to drop it just like this. So that's what they did. So this entire paper is for the purpose of justifying what they did, the path that they took, meaning using the Clark method in the new generation of spatially distributed data, GIS, radar, etc. Historical considerations, Clark's original methodology, we don't have to stress on that. We have already seen it. Okay, this is, you see what they're doing there, the basin shape, the time area histogram. That's exactly what I did, or I tried to do with Andrea Scott. Spatially distributed watershed information. This is all electronics already. And runoff calculation. Like and look at the way they did it. And I'm going to finish it here in a minute. They brought the watershed into squares. And then they applied a Clark method to each square. I cannot tell you exactly how they did it because I don't know. I would have to get into the model. And they don't allow you to get into the model for one thing. The Army Corps does not discover, or rather reveal source code. They do not reveal source code. They give you a compiled execution of HMS, which you can run, but you cannot ask questions. As a matter of fact, the policy is don't ask me questions. Anybody that wants to ask questions runs into a wall of cement or concrete. As a matter of fact, I have done that. At one time, many years ago, I tried to ask a question. I tried to call somebody out there. They don't answer the question. They are not in the business of providing service. They are no business anyway. They're a federal agency. They don't provide service. What they do is they recommend kind of softly that if you don't understand the processes, you hire a consultant. You pay a consultant. There are many consultants out there. They're all presumed to know. So you can hire a consultant if you don't know, or you can go back to school, or you can sit down and spend 3 months learning this stuff, but you're not going to get the source code. So exactly what they did, that's a mystery. They are the Army Corps. Whatever they did is accepted one way or the other. I am not being negative. I'm being like statement of fact. That's just the way it is. Okay, with that, I am going to finish in here, and I'm going to stop the share. And as it is customary, I say, you know, if you have any questions at this point, I wouldn't hesitate to answer maybe one question. And if not, then my advice to you is reread, revise everything we had said, because it may be on the final exam. I'm not going to ask you to do a calculation in the final exam, but I'm going to ask you about concepts and the procedures and techniques, and even the history, because I've dwelled on the history extensively. Because first of all, I like it, and second of all, if you don't know the history of something, how are you going to pretend or purport to understand it? Everything has history behind it, and I actually dwelled on it because it's important to know the origin of things that we do for calculations.